Okay, let's jump right into this. Welcome to this explainer, where we are going to completely decode the immense hidden power of ocean currents and how they literally sculpt our coastlines. You know, if you've ever wondered why some beaches feel like absolute tropical paradises, while others at the exact same latitude are freezing cold, well, you are in the right place. We're going to break down the massive forces moving our oceans and shaping the land we live on.
Here is our roadmap for today. We'll start with number 1, the latitude mystery, then move into 2, global heat redistribution. Next, we'll uncover 3, the 3 drivers of currents. We'll look at 4, a tale of 2 coasts, explore 5, impacts on coastal weathering, and finally wrap things up with 6, ranking coastal influences.
Let's kick things off with part 1, the latitude mystery. So, here is a massive geographical puzzle for you. Think about the movie Titanic. How on earth could Jack freeze to death in waters that share the exact same line of latitude, 51 degrees north, as places like Cornwall in the UK, a spot completely devoid of sea ice? Geographically speaking, they are at the exact same horizontal position on the globe, meaning they should technically receive similar amounts of solar radiation. Yet the realities on the ground, or in the water, are wildly different.
When we map out the sea surface temperatures for this latitude, the colors tell the whole story. The incredibly warm waters bathing the UK contrast so sharply with the freezing, icy waters hugging the coast of Canada, all along that exact same 51-degree line. This perfectly proves that thermal inputs into our oceans completely dictate our coastal environments. It totally overrides simple latitude.
Which brings us to section 2, global heat redistribution.
To understand that extreme temperature difference, we have to zoom way out and look at the offshore zone on a global scale. Ocean currents essentially act as massive, planetary conveyor belts. You have warm currents originating near the equator, moving out to warm up specific coastlines, and cold currents that drastically cool down others. They don't just sit there. This is a large-scale, constant movement of water.
The crucial takeaway here is that these vast movements of water are constantly working to redistribute heat energy across the entire planet. They are literally the Earth's thermal balancing system, pulling excess heat from the tropics and dragging it all the way up to the freezing polar regions.
All right, part 3, 3 drivers of currents.
So, what exactly provides the engine for this huge planetary heat transfer? I mean, moving billions of gallons of water across the globe requires incredible force. It really comes down to 3 primary drivers: surface winds, the Coriolis Effect, and Thermohaline circulation. Let's unpack those last 2, because they are fascinating.
First up is the Coriolis Effect. Because our Earth is a spinning sphere, it fundamentally alters the shape and trajectory of our oceans. Water doesn't just flow in a simple straight line from the equator to the poles. The very rotation of the Earth beneath the water actually deflects it.
As the Earth rotates on its axis, the path of the moving water is physically bent into a curved trajectory. This rotational force is exactly why ocean currents often look like they're moving in sweeping, circular motions rather than straight lines. It's like trying to draw a straight line on a spinning record.
Then we have a deep water mechanism called thermohaline circulation. Now this happens up at the polar regions. When sea ice forms, only the fresh water freezes, which leaves all the salt behind in the liquid ocean. This produces seawater that is highly saline and incredibly dense. Because it's so heavy and freezing cold, it physically sinks right down to the bottom of the ocean. And this action builds into a massive global system known as the Great Ocean Conveyor Belt. That sinking action of the dense, salty water is absolutely crucial. As it sinks deep into the abyss, it acts like a giant vacuum or pump, actively pulling the shallow, warmer surface waters northward to replace the cold water that just sank. This continuous planetary-scale loop is vital for moving both heat and nutrients around our entire globe.
Moving on to section 4, a tale of 2 coasts. Now let's apply these global mechanics to our specific comparative case study. This stark juxtaposition between a west-facing coast in the UK and an east-facing coast in Canada is what actually solves our Titanic mystery. We have to look at the combination of the ocean current itself and the direction of the prevailing winds. Over in the UK, west-facing coasts like Cornwall are constantly bathed by the warm North Atlantic drift. But remember, it's not just the water, it's the wind too. The prevailing winds are onshore, meaning they blow from the ocean toward the land. As these winds travel over that warm ocean current, they act like a giant heater, blowing a massive amount of warmth directly onto the British shores. Conversely, let's look at Canada's east-facing coasts. They are chilled by the freezing Labrador current, which carries sea ice straight down from Greenland. Yep, that's exactly where the Titanic met its fate. The winds here actually blow offshore, away from the land. But the real kicker happens in winter. The massive frozen North American continent cools the air, creating a freezing polar continental air mass that just camps right over eastern Canada.
Let's look at what this means for the rocks in Section 5. Impacts on coastal weathering. Because of that steady, warm thermal input from the onshore winds and the North Atlantic drift, Cornwall simply stays too warm for freeze-thaw weathering to take hold. You just don't have water constantly freezing in the cracks of the rocks and expanding. And because there's so little frost shattering, the amount of sediment breaking down into the ocean is severely reduced. The cliffs are essentially protected by the warmth.
But on the other side of the Atlantic, it's a completely different story. The freezing winter conditions in Labrador put freeze-thaw weathering into hyperdrive. The constant freezing and expanding of ice inside the rock joints vastly increases the amount of shattered, weathered material physically falling off the cliffs. This dumps a massive flow of sediment directly into Canada's coastal landscape systems.
Finally, let's bring it all together in Section 6, Ranking Coastal Influences.
We've covered a huge range of physical factors today: winds, waves, geology, tides, ocean currents, sediment cell boundaries, and sources of sediment. But a high-level geographical analysis doesn't just list these factors out. The really fascinating part is evaluating which of these forces truly dominates the landscape.
I highly encourage you to try a quick thought experiment. If you had to rank these influences from 1 to 7, what goes in the number 1 spot? Don't just pick a random factor, you have to justify it. Think about whether a massive global force, like an ocean current, always dictates the landscape, or if immediate local factors take over.
So, as you wrap up your notes from this explainer, I want to leave you with this final critical question. When evaluating a coastal landscape, which physical factor is ultimately the most dominant? Does a massive global force like an ocean current always override a local factor like rock lithology? It's something to think about next time you're standing on a beach. Thanks for joining, and we will see you in the next explainer.